Yes. So the type of data we usually most often collect on our questionnaire would be ordinal, interval, and ratio data. And this is these are values, as we said, values. The only thing that separates interval and ratio data is the presence of an absolute zero. And so, for instance, if I ask about age, your age cannot go below zero. If I ask about height, I ask about weight, those values cannot go below zero. But if you ask about temperature, for instance, temperature goes well below zero. You ask about profit, you can have a negative profit. So the thing that separates interval and ratio data is the presence of that absolute zero. And so once you can have an absolute zero or not, that's the thing that separates those two. And so these types of data are treated very differently in analysis. So every measure is not appropriate for every type of data. And we're going to see that as we go on. And so you also take into consideration the nature of the underlying distribution. So when we talked about data, we also separated it, variables, we also separated them by discrete and continuous. And I would be very happy if somebody could remind me what is the difference between discrete variables and continuous variables. Any takers? Right, so one of those types of variables, the values are finite and countable and only result in whole numbers. And one of that, the other type, is not countable, is not finite, and the variables can take on any value within a given range. So which is countable and finite, discrete or continuous?
Discrete.
Right, so your discrete variables are those countable variables: number of males, number of females, number of cars, number of houses, and you only count complete things. You can't have 1.5 person. But your continuous variables are those variables for which the values are not countable. They can take on any value within a given range. So you look at volume, for instance, weight, those variables that we tend to round. So if you ask weight, you probably round, if you get 109.8, you probably round it to 110, but the weight is not 110. And so weight can take on any value within a given range. And if you want your data collection to be accurate, then you will not round. Same for height and so on. So it depends on that. It also depends on whether the distribution is linear or non-linear. Linear meaning that it follows a straight line. When you plot it on a graph, you can see generally a trend towards a straight line. If it's non-linear, it's more of a curve. So those curves, those normal distribution curves you've been plotting, those are non-linear distributions, non-linear continuous distributions. Now, the linear would look more like a straight line, and the correlation, that is applicable only to linear values. And so we continue. Any questions up to this point? All right. Okay, great. So there are two types of correlation. There are two measures of correlation which we'll look at. One of them is the more commonly used. That's the Pearson's R, or what we call the Pearson's product moment correlation coefficient. And so this is a measure of the linear or straight line relationship between two interval level variables. Now, remember on the previous slide, we just said that the measure you use depends on the characteristics of the data. And so this is saying clearly that this particular type of this particular coefficient can only be calculated for linear relationships, and it can only be done for interval level variables. So if you have any other type of data, you need to find another measure because the Pearson correlation coefficient is not going to be applicable. So the form of the relationship between the two variables can be presented visually on a scatter diagram. And so this is the first thing we usually do to test for linearity. So can we use the first question we ask, can we use the correlation coefficient? And in order to answer that question, you plot a scatter diagram. And based on what you observe on that diagram, you're able to determine whether or not the correlation is an appropriate measure. Now, this is a graph that has two axes, X and Y. And the X-axis, and most of you have done economics by now, ECN 1100.
Yes, miss.
Excellent. Excellent. So you know that the X-axis is usually reserved for the independent variable, whereas the Y-axis is reserved for the dependent variable. And so with your correlation, it's two variables, you're looking for the relationship between, and you usually have to determine which of those variables is dependent and which is independent. And since all of you have done in ECN 1100, then one of you should be able to tell me what is your dependent, what I mean when I say dependent variable as opposed to independent variable.
Independent would be the cause variable, and the dependent would be the effect variable.
Right. That was Jason.
Yes, miss.
Excellent. So cause and effect. So the independent variable is the variable that is affecting or causing some effect in the dependent variable. So your dependent variable is determined by changes in the independent variable. And so in your economics, you would have looked at, for instance, price and quantity demanded. Price being the independent variable because depends on the price that will determine how much people buy or what the quantity demand is going to be. So it's similar to that, except that we're looking at different variables. And so when you plot your, when you calculate your Pearson correlation coefficient, it can take on any value between a positive 1.00 and a negative 1.00. Now, either the positive 1 or the negative 1 represents a perfect relationship between these two variables. The sign in this sense is only important because it tells you the direction of the relationship. Direction of the relationship meaning whether the two variables are related in a positive way or a direct way, or they're related in a negative way or an inverse way. And so I just mentioned the example of price and quantity demanded. As price goes up, more often than not, quantity demanded goes down, and as price goes down, quantity demanded goes up. So that is showing you an inverse relationship. So if you were to calculate correlation for those two variables, you're going to end up with a negative value. And that negative value tells you the direction of the relationship. So as one variable is increasing, the other variable is decreasing. Whereas a positive sign would tell you the opposite, that they're moving in the same direction. So when one goes up, the other also goes up. And so when you plot your scatter diagram, the closer the points appear together, the closer you can see it resembling a straight line. That tells you before you even do the calculation. Since you look at the diagram, you get a sense of how strong is the relationship between these two variables. And so it's usually a good starting point to start by plotting your diagram. Now, when you do calculate your coefficient, how do you interpret it? And so what we have here on this slide is the general guideline in terms of how we interpret the values. And so if your coefficient is somewhere between 0.00 and 0.19, and this is either positive or negative, doesn't matter if it's a negative 0.19. So between 0 and 0.019 is a very weak relationship. There's some relationship, but it's very, very weak. Between 0.0 0.20 and 0.39, that is weak. It's not very weak, but it's still weak. You'll find a moderate relationship if your coefficient is between 0.40 and 0.59. And you will find a strong relationship if your mesh is between 0.60 and 0.79. And if it's anywhere above 0.8, then it's very strong relationship. And so this is handy to keep right in your book. Keep it at a point where you can easily refer to it, because once you've done your calculation, this is what's gonna guide you in terms of interpreting those values. Now, the first example we wanna look at, we have two variables. We have our x variable, and as we said earlier, x represents the independent variable. So you have the mother's education as the x and the daughter's education as the y. Now, this is looking to see whether there's a relationship, and if there is a relationship, how strong is that relationship between the number of years of schooling a mother has and the number of years of schooling her daughter has. And we're using mother's education as the independent variable to suggest that the number of years of schooling the daughter will have is somehow dependent on the number of years of schooling the mother has. Now, that can be for any number of reasons, but the thinking is that the daughter's education is dependent on the mother's education. And so what we have those two variables. Now we're gonna see the formula, and we're gonna see why we needed to add those other columns. But for now, those are our two variables. And like I said, the first thing you usually want to do is a scatter plot. Now, two things the plot tells us. It gives us a rudimentary glance as to the strength of the relationship. And we can see from looking at this graph that the points are very spaced out. We can see it generally going in an upward direction, but it's not very strong. The points are not very close together. You can't get a good straight line from here, but you can see that generally it's going upward. So it gives us a sense of the strength, but it also gives us a sense of the direction. So we can see that this is generally going in an upward direction. So if we were to impose a line here, and if we were to calculate the correlation coefficient, we would expect a positive value, because these two variables seem to be related in a positive way, meaning that as the mother's education increases, the daughter's education also increases. Now, that can be for any number of reasons. It can be that the more educated the mother is, the more motivated she is to ensure that her daughter is educated. But it can also be that the more educated the mother is, the more motivated the daughter herself is to emulate her mother or even surpass her mother. And so the level of education of the daughter is dependent in a positive way on the level of education of the mother. So as one goes up, the other is also going up. So that's what the plot is telling us. When we see it going in this general upward direction, tells us that we're to expect a positive sign when we calculate our correlation coefficient. Am I clear up to this point?
So far, Miss.
Okay, great.
Miss, just a quick question back to the graph. I'm sorry I joined the class late tonight. You're saying here for the points that are already plotted. I'm looking back at the table X and Y. Just explain back this part here because I'm not clear. I want to know, why is it that the only two values we have for X and Y, why is it that it's not separated for the mother and the daughter? And when you put them together, it's like this. I'm not very clear here.
So have you done, you haven't done ECN 1100?
Yeah.
So you understand the basics of plotting a graph. So you have,
Yes.
so you have two variables. You have the mother's education, and you have the daughter's education. Mother's education is the x variable, meaning that is on the x-axis, and you know which axis is the x-axis. Do you know which axis is the x-axis? Anybody?
Yeah.
Right.
Horizontal.
And the y. So you have pairs of values. Specifically here, you have 7 pairs of values. And so you can see that at the first point, we can call this point A. The value of the mother's education is 1. The value for the daughter's education is 7. And so we can see here on our x-axis, we're using a scale of 2. And on our y-axis, we're using a scale of 5. So this point here represents that point of 1 for x and 7 for y. Likewise, this point would represent the second pair of values, and so on. So you should have 7 points on this graph that corresponds to these 7 pairs of values that you have here for x and y. Does that answer your question?
Clear. Thank you.
Great. Right, so the formula that we use for calculating the correlation coefficient, the Pearson correlation coefficient, R, so the Pearson correlation is R. So when you see R, say you're reading a research paper and you just see the correlation coefficient represented as R, then they've used, this is the formula they've used. So the formula is n times the sum of xy, n being the number of pairs of values that we have, and we just saw from our table that we have 7 pairs of values. So it's n times the sum of xy minus the sum of x times the sum of y. So the sum of xy is what we get when we multiply x by y, and we total that column. So that is the sum of xy. And then we also have to sum the x's, and we have to sum the y's. So it's n times the sum of xy minus the sum of x times the sum of y. And we're dividing that by, now everything at the bottom of this formula is in a square root or under a square root sign. So it's the square root of n times the sum of x squared. And when you see x squared without a bracket, it means that you're squaring all the x's and you're taking the total. So it's n times the sum of x squared minus the sum of x in bracket squared. That means that when you see the sum of x in a bracket and then the square outside of the bracket, it means that you're summing the x, the column that says x, you're summing that column, and then you're squaring the total rather than squaring the individual values. That's what you do over here. So again, it's n times the sum of x squared minus the sum of x all squared. And then we times that by n times the sum of y squared, which again, you square the individual y's and take the total to get this value. So it's n times the sum of y squared minus the sum of y, and then we square that value. So we total up the column that says y, and we square that value. So it's n times the sum of y squared minus the sum of y, and we square that value. So this formula, if you break it up into its respective parts, it's actually very easy to remember. So at the top, you have the xy. So it's n times the sum of xy minus the sum of x times the sum of y. And at the bottom, you have the x's and then you have the y's. So it's n times the sum of x squared minus the sum of x squared times n times the sum of y squared minus the sum of y squared. So in its respective parts, it's a pretty easy formula to remember. It just looks a little bit long because it has so many components, but the way it's organized, it's actually very convenient. So I'm gonna go back to the table. Right, so we have the x, which is the mother's education, and we've totaled the x's, the column, we've totaled the values here, and we found the sum of x to be 49, The y here is the daughter's education. We've totaled that. And as you see the formula, so the formula requires a sum of x. It requires a sum of y. It also requires a sum of x squared, which we get from squaring these individual values. So we square 1, which gives us back 1. We square 3, which gives us 9. 5 gives us 25. 7, 49, and so on. So we square all the x's, and likewise for the sum of y squared, we square all the y's. It also requires the sum of xy, and so we times the x, we times the x times the y. So that gives us 7, 4 3 is 12, 5 by 13, 65, and so on and so on, and we total the columns. So what you add to this table, depends on what your formula requires of you. And so coming back to this formula, it's n. I said earlier that n represents the number of pairs of values that you have in the data set. And in this case, we have 7 pairs of values. And so n is 7 times the sum of xy, which was calculated in the table, minus the sum of x times the sum of y. And then at the bottom here, you have that square root that covers everything. So it's n times the sum of x squared minus the sum of x. As you see, this value is always going to be the smaller value because it's what you get from adding up the x's. You square that. Times n times the sum of y squared, again, minus the sum of y, the smaller value, squared. And so once you've identified these specific, once you've totaled these columns and gotten these values, the rest of it, you minus the top, and then you minus this bracket, you minus that bracket. You multiply the values in these two brackets, you divide what you get, and that gives you your correlation coefficient, which turns out to be 0.82. Now, if we go back to this table, we see that 0.82 gives us a very strong, tells us that the relationship between the mother's education and the daughter's education is a very strong relationship with a correlation value of 0.82. And so this is not a hypothesis testing topic. It's just a topic that looks at measures of association between variables. In this case, the two variables we're interested in, mother's education, daughter's education. And from what we're seeing from this data set, there's a very strong positive relationship between these two variables, the mother's education and the daughter's education. So, gonna stop here and ask for questions. I think I'm running out of time on this first call. I sent you 2 links. So when this one ends, you're just gonna open the second link and we're gonna continue. So are there any questions before I wrap up or before I end this part? And then we start back. We're gonna continue and look at another example and then look at some other things. Does anyone have any questions?
No, miss.
All right, so I'll just keep going until they end it. So we have another example here. Now, before I go to this, what I would like you to do for the next class, I want everybody's going to make a presentation in the next class. So everybody is going to think about, I'll send you some calculation things to do as well, but this particular part of the exercise, everybody's going to do individually. So I want everybody to think about, start to tell me how you would do a correlation, but it starts with 2 variables that you are interested in studying. And you have to look at these things. You have to look at the type of the scale of measurement. Is it a nominal or ordinal or interval or a ratio variable? Is it discrete or continuous? And do you expect it to be, well, this part, the data will tell us. So you don't necessarily have to do that. But at least tell me The scale of measurement and the nature of the distribution, is it a discrete or continuous? And so two variables that you're interested in, and then you're going to describe it by talking a bit more about those variables. And so we'll just have that as a discussion point, and then we're going to do, so I'll send you some practice questions on this topic, and then we'll look at those as well to see how you did and if you have any questions, if anything is still unclear at that point. So is everybody clear on what they're supposed to be presenting next class? It's just going to be about 5 minutes per person.
Mr. Breaking up, what per person?
Right.
Sorry.
Are you hearing me better now?
Yes.
Miss, is it possible you can put it together in like a little email and send it to us so we have a better understanding? Their connection is a little poor.
Oh, yeah, it's raining, so that's probably
Yes,
contributing
it is.
to it. So
Mhm.
I can do that. I'll send it to you because I still have to send you a worksheet and I have to send you the recording. I think I remember to record this time. Shoot, there are 3 people waiting to be. Oh, it's in the chat. Right, so I have to send you the recording and I have to send you the worksheet. So I'll just add that as the first question on the worksheet. So.
Thank you.
Great. Okay, good. So as we still have connection, let me just go on. So we have two other variables. We're looking at score, a student's performance on one specific exam and their overall grade point average. Now, these are not values from UG, so don't be alarmed by these 0.5 and 1 and 1.5 and so on for the grade points average. So, but generally, the researcher wanted to know whether there's a relationship between how a student performed in statistics and their overall grade point average. And similarly, we use the score on the statistics exam as the independent variables. We're gonna presume, we make a lot of assumptions when we're doing research, but we're gonna presume that a student's performance in statistics, as just one example of a course, is their GPA depends on how well they do, because generally your GPA depends on how well you do in every subject. And so that relationship is pretty much established, that your performance in a particular subject determines what your GPA is going to be. So GPA tends to be dependent and your performance in the individual subjects tend to be independent because those will determine what your GPA turn out to be. So you have the exam score as the X variable, the grade point average as the Y variable. Your formula requires you to have the sum of X squared. So you have to square all these individual X's in this column. And it also requires you to have the sum of Y squared. So you have to square all these individual Y variables in this column. And then it requires you to have the sum of XY. And so you're gonna times the X's by the Y's, X times Y, and then you're gonna total up that column. So you fill up the table. It's usually the easiest thing to do. So you just fill that out. I shouldn't say easiest, but most convenient thing to do. Once you see the table, you complete it because you know what your formula requires. You complete it, and then you go on. Now, you want to also do your scatter plot. You can do this before you do the calculation. That's perfectly, that's actually preferable. And so if you look at this scatter plot as compared to the one that we had before, you can see that the points are much closer together and you can see a much clearer line you can see much clearer indication of a straight line relationship here between these two variables. Using, again, you see GPA on the y-axis, the score on statistics on the x-axis. And so your independent and then your dependent variable, you want to maintain that when you're plotting the diagram. And then again, we come back to the formula. And so again, it's n times the sum of xy times the sum of x times the sum of y. And then divide that by the square root, n times the sum of x squared minus, there's a minus sign missing here, the sum of x squared. And then we multiply that by n times the sum of y squared minus, again, the sum of y squared. And remember,